Let's continue with another advanced machining process. This is called as electrochemical machining. It has some similarity with respect to the previous one, but a bit different, I can say. Let me describe this process first on this sketch. This is a simple schematic of an electrochemical machining you see. Again, we have a tank, and this time instead of an agent or reagent, we are using an electrolyte liquid here, and we put our workpiece inside this tank once again. But this time we don't need to have a workpiece carrier. We can simply put our workpiece onto the surface of our tank. But the difference is that we are applying some currents into these actually in this let's say machining process, advanced machining process. In the previous one, in the chemical machining, we don't have any current flowing between the workpiece or inside your tank. So what we have in order to have this current flow, we have our workpiece as the anode, and then we have our tool, which is the cathode of our arrangement, and current is always flowing from this cathode or the tool to the workpiece. And during this movement, actually, with the help of some here, actually heats increase and some chemical reactions, we can remove material from the workpiece. And it's actually the reverse of electroplating issue, electroplating process. So the rest is somehow similar. And another important issue, we need to supply this electrolyte actually uh, into right into the machining zone. So that with the help of this, we can transfer currents from the tool to the workpiece, and also with the help of this pumping action, we can remove these generated chips, or what we call them as debris, or very small, tiny chips. And obviously, this process can only be applied on metals or the conductive materials, I can say, since current should be flowing from the tool into the workpiece. And our electrolyte actually acting as a current carrier, since otherwise it will not be a complete circuit. This is one of the functions of electrolyte, let's say, liquids. Another issue is that the cavity is actually this cavity is the mating surface of our tool. You see, we have a circular section at the tip of the tool, and we have a similar shape inside our workpiece. So if you want to have complicated shapes, then you need to design your tool according to your needs, and then do this electrochemical process. And we can say about the material weight is that it highly depends on the amount of current. So if you increase the current flowing through this tool and the workpiece, then you will be removing more material, and you can see some typical values of current, sometimes up to 200 ampere, and the voltages are not too high. And where we can use this process with the help of actually such a process, such current flowing through the tool and the workpiece, we can machine very large, very complicated shapes. But the thing is that we need to design, manufacture the tool again ourselves, since if you have a custom shape in your company, then probably you cannot use the universal tools. You need to design yourself and then manufacture your tool. But for, as I said, complicated shapes, for stronger products, materials, harder materials, it's better. This process is highly useful compared to machining processes. Here are some example parts and tool here, as you see. This is the tool we are using in the electrochemical machining process. And before this process, this is a V shape we have. And once we do electrochemical machining, our tool will be going into this workpiece and open such grooves on these side surfaces. And furthermore, you can have such more complicated, much more complicated shapes. Uh, the thing is that you need to have the properly designed tool in your process. We have a bit different version of this electrochemical machining. Is called as shaped electrolytic machining process, but the idea is the same this time. It's mostly developed for actually tubes for actually machining very thin and long holes or such larger holes. But the idea is the same again. We have an electrolyte and this is flowing through the tool inside the tool, and again uh, with the help of the current flowing through the tool into the workpiece, we remove material. And now let me talk about another advanced machining process. This is called as electrochemical grinding. You'll see it's somehow similar to our conventional grinding. So that's why actually it's only doing some conventional grinding and also some electrochemical machining. That's why it's named as electrochemical grinding. It's combining the functions, the main principles of electrochemical machining and grinding process. And obviously, we need to have a grinding wheel here as you see, and it is this time not only a grinding wheel, but it's also the cathode in our electrochemical machining process. And again, our workpiece is the anode, and we'll be again applying currents through the circuit and try to remove material from the surface or from specific regions of our workpiece. And another thing is that on this grinding wheel, obviously, we need to have some actually uh, abrasive particles, embedded abrasive particles. And again, as in the case of electrochemical machining, we need to supply electrolyte. And as you see, there's a hose, and this is connected to the pump. So we are continuously supplying this electrolytes over into the cutting zone. And what are the actually abrasives are doing here on the grinding wheel? Obviously, they are removing metal, but not too much. Their main function is actually to act as an insulator between our wheel and the workpiece material. And in this process, most of the machining, actually most of the material removal is done with the help of the electrolytic action. So we can say that it's about removing material for most of the time with the help of electrochemical action, but it's only removing 5% of the time with the help of grinding action. And that's why actually the grinding ratio is very high. We don't have much wear on the grinding wheel, so you don't need to replace it frequently. Even you can use it on very harder materials like as this one here. They have opened a kind of a groove into the cylindrical part, and this is made of Incona, which is a very hard material, a difficult to machine material. So in such cases, you may go with electrochemical grinding since we have less weight on the grinding wheel, and we can produce such difficult shapes, grooves, or increase the surface quality, dimensional accuracy of the parts. Let's continue to another advanced machining process. This is called electrical discharge machining, and as the name implies, again, we need to be working on conductive materials. For other ones, it's not possible to do this, to employ this process. And what we are doing in this process, how we are removing material, we remove metal with the help of actually sparks generated in between the tool and the workpiece. So metal parts are actually eroded and they are evaporated, and we will be, if you repeat this process, let's say a million times, then little parts, little debris will be removed from the workpiece, and you will have the desired shapes. This actually depends on the fundamentals of two wires carrying current. If you touch these wires together, then you will have a spark generated, and after the spark, you have little material removed from the tip of these wires. And this is the fundamental, actually the principle, main principle we are using in electrical discharge machining. And it's one of the most actually popular advanced machining processes. Many companies are using this type of process for difficult to machine materials. I can show you the fundamentals over the schematic. Again, we need to use a kind of a fluid, but this time the fluid is named as dielectric fluid. And you can see that our again workpiece and the tool is connected to our power supply. And again, our actually opening will have the same shape with the tool, so it will be the mating surface of the tool. And again, as in the case of previous electrochemical machining, we are moving our tool into the workpiece and open a kind of an, let's say, shape. But the thing is that in this, in between the tool and the workpiece, this time we have a bit complicated process. We have sparks generated, but how these sparks are generated? If the potential difference is not high between the tool and the workpiece, then our dielectric fluid is actually acting as an insulator. So we cannot transfer current from the tool into the workpiece. But once the potential difference becomes high, which means that the gap is decreased, in that case, we will have current actually flowing from the tool into the workpiece. And during this motion, we will have a spark generated, and with the help of the spark, the temperature of this region will be increased a lot, and our metal will be melted, and some parts will be removed from the surface. And assume that this actually happens about 500,000 times in a second. So with the help of these, we can remove material and from these very difficult materials and have our desired shapes on the workpiece. And obviously, due to the actually gap between the tool and the opening, you will always have overcuts. So the designers should be aware of this issue and design or manufacture their tools accordingly. Let's have a look at the functions of this dielectric fluid in between the tool and the workpiece. First of all, it should be acting as an insulator before these sparks are generated, and it should be actually decreasing the temperature of the workpiece and also the tool, so it's a kind of a cooling medium. And lastly, it should be removing all these chips, actually debris and the gap. So these are three main functions of the dielectric fluids. What are actually these? We can use mineral oils, but the easiest one is actually deionized water. We can use such water in electrical discharge machining process. And the electrodes are highly important in this process. There shouldn't be too much wear. Otherwise, you may need to replace your electrodes even during the process. By the way, electrodes are actually the tools we are using in this process. They are sometimes called as electrodes, and we can manufacture them using different manufacturing operations, and they are mostly made of graphite, brass, or copper, and different alloys may be used in this in the manufacturing of electrodes. And with proper actually electrodes, you can even open holes with a length of 400 and with a diameter of 1 unit. So this is a quite high number. You cannot achieve it with other processes. And as I said, if you do not select the right material for your electrode, then there might be too much wear on your electrode. And this is called as wear ratio, very similar to the grinding ratio. In order to decrease this actually amount of wear on our tool, what we do, we try to use materials having higher melting point. So if your electrode material has higher melting point, then that means it will be quite difficult to remove your electrode, and you will be using it for a longer time. And we have a different version of this electrical discharge machining. It's called as wire EDM, and as the name implies, as opposed to complicated tools, electrodes, what we are using wires. And these wires may be made of, again, brass or other kind of materials. But the thing is that, as you see, it's moving continuous over our workpiece, inside our workpiece. In addition to these movements, we are also moving it along our path. so that a specified contour will be machined, will be removed, and maybe we can remove complicated shapes out of it, or divide our workpiece into several smaller workpieces. And again, in the case of EDM, electrical discharge machining, we need to have dielectric fluid, but this time, since if you're not doing the machining, the process in a tank, you need to be supplying this fluid continuously into the cutting zone. And this is very similar to actually solving process, and that's why again we have a kind of an curve, and this curve happens actually due to the wear on the all regions, on the all surfaces, side surface and front surface of our opening. And we know that there also happens wear on the tool, on the wire, so we need to be careful about it. But this is a nice process for actually obtaining 2.5D shapes, complicated 2.5D shapes. And we have a last type of electrical discharge machining process. This time it's about grinding. We are using the same principles of grinding, conventional grinding, but this time instead of only rotating the grinding wheel and moving it over the surface, what we do, we need to apply obviously currents, and we need to be applying, supplying some dielectric fluid in between the wheel and the workpiece. And with the help of this again, we are going to remove material with the principles of electrical discharge machining, and you maybe remove little material with the help of conventional grinding principles.